Hello and welcome. In this video, we will show you how to build a convolutional neural network using TensorFlow. We'll also train the network on the MNIST dataset, which is a large collection of handwritten digits. All of the following code cells will be run in an interactive session in the Jupyter Notebook. Let's retrieve the MNIST data. We'll then create the general parameters for our model. And we'll create placeholders for the inputs and outputs. Next, we'll define a function to generate weights. It's important that the weights have a small amount of noise and that we prevent gradients with a value of 0. After the weights, we'll define a function to generate biases. An important note about the ReLU activation function is that neurons can be very sensitive during training. If a large gradient flows through a ReLU neuron, the weights could be updated in such a way that the neuron will never activate on any data point. To avoid these dead neurons, we'll set slightly positive initial biases. Afterwards, we'll define a function to create the convolutional layers. Then define a function to perform max pooling. Max pooling is an operation that finds the maximum values and simplifies the inputs using spatial correlations. The kernel size is 2 by 2. If the image is a 2 by 2 matrix, the output would be 1 pixel. The strides will dictate the sliding behavior of the kernel. In this case, it will move 2 pixels every time without overlapping. So this is our first convolutional and max pooling layer. Let's now set the weights and biases. Our kernel size is 5 by 5, we have 1 grayscale input channel, and we have 32 feature maps. Now we need to convert the images of our dataset into tensors. The images are 28 pixels by 28 pixels, and again, since they're grayscale, there's only 1 channel. In this case, the first dimension is the ID number of the image, which is just the input's position. Because of the -1, there is no size limit. Next, we'll convolve with the weight tensor and add the biases. And then we'll apply the ReLU activation function. Here we apply the predefined max pooling operation. With that, we completed the first layer. We'll move on to the second convolutional and max pooling layer. Again, we'll set the weights and biases. The kernel is 5 by 5. We'll have 32 input channels since the first convolutional layer had 32 feature maps, and we'll have 64 output feature maps. We already converted the images into tensors during the first layer phase. Again, we'll perform a convolution with the weight tensor and add biases. Then apply the ReLU activation function, and apply max pooling. And we completed the second layer. For the third layer, we're going to create a fully connected layer that will use the softmax function. This way the network will eventually be able to generate probabilities for its classifications. So as usual, we'll add weights and biases. Based on the last layer, we need to multiply the 7 by 7 feature map by the number of feature maps, which is 64. The softmax layer will have 1024 outputs. Then we'll flatten the second layer. Use matrix multiplication to apply weights and biases. Apply the ReLU activation function. And we completed the third layer. We can optionally use a strategy called dropout, where we intentionally cause the network to forget some of the features. This may help prevent overfitting, although not everyone agrees that this is the case. The final layer of the network is the readout layer, and it will also be a fully connected layer with the softmax function. It will need 1024 input channels due to the size of the third layer, and 10 output features. This will form our classification probabilities for each of the 10 digits. We'll use matrix multiplication to apply the weights and biases. We'll apply the softmax function, and that's it. There's a lot of layers to keep track of, so here's a brief overview. We start with the input from our dataset. Then we have two convolutional and max pooling layers, a fully connected layer, our dropout layer to prevent overfitting, the readout layer to generate probabilities, and then the outputs themselves. At this point, we're ready to train the model. So we can define the loss function, define the optimizer, define the prediction, define the accuracy, then run the session and train. And you may want a fast result since training does take some time. If you'd like, you can run even more iterations, though this will demand more time. And finally, we can evaluate the model. At this point, you should understand how to implement a convolutional neural network using Tensorflow. Thank you for watching this video. To practice and learn more, go to the lab and run the code for yourself.